In number theory, a perfect number is a positive integer that is equal to the sum of its proper positive divisors, that is, the sum of its positive divisors excluding the number itself. Equivalently, a perfect number is a number that is half the sum of all of its positive divisors, i.e., sigma 1 equals 2n. This definition is ancient, appearing as early as Euclid's Elements, where it is called tau epsilon lambda epsilon iota omicron sigma rho iota theta mu omicron sigma. Euclid also proved a formation rule whereby is an even perfect number whenever is what is now called a Mersenne prime. Much later, Euler proved that all even perfect numbers are of this form. This is known as the Euclid-Euler theorem. It is not known whether there are any odd perfect numbers, nor whether infinitely many perfect numbers exist. Examples: the first perfect number is 6, because 1, 2, and 3 are its proper positive divisors, and 1 plus 2 plus 3 equals 6. Equivalently, the number 6 is equal to half the sum of all its positive divisors. 2 equals 6. The next perfect number is 28 equals 1 plus 2 plus 4 plus 7 plus 14. This is followed by the perfect numbers chapter 496 and 8128. History. These first four perfect numbers were the only ones known to early Greek mathematics, and the mathematician Nicomachus had noted 8128 as early as 100 AD. Philo of Alexandria, in his 1st century book, On the Creation, mentions perfect numbers, claiming that the world was created in 6 days and the moon orbits in 28 days because 6 and 28 are perfect. St. Augustine defines perfect numbers in City of God in the early 5th century AD, repeating the claim that God created the world in 6 days because 6 is the smallest perfect number. In a manuscript written between 1456 and 1461, an unknown mathematician recorded the earliest reference to a fifth perfect number, with 33,550,336 being correctly identified for the first time. In 1588, the Italian mathematician Pietro Cataldi identified the sixth and the seventh perfect numbers, and also proved that every perfect number obtained from Euclid's rule ends with a 6 or an 8. Even perfect numbers. Euclid proved that 2p-1 is an even perfect number whenever 2p-1 is prime. For example, the first four perfect numbers are generated by the formula 2p-1, with p a prime number, as follows. For p equals 2. 21 equals 6 for p equals 3, 22 equals 28 for p equals 5, 24 equals 496 for p equals 7, 26 equals 8128. Prime numbers of the form 2p-1 are known as Mersenne primes, after the 17th century monk Marin Mersenne, who studied number theory and perfect numbers. For 2p-1 to be prime, it is necessary that p itself be prime. However, not all numbers of the form 2p-1 with a prime p are prime. For example, 211-1 equals 2047 equals 23 times 89 is not a prime number. In fact, Mersenne primes are very rare. Of the 9,592 prime numbers p less than 100,000, 2p-1 is prime for only 28 of them. Over a millennium after Euclid, Ibn al-Haytham circa 1000 AD conjectured that every even perfect number is of the form 2p-1 where 2p-1 is prime, but he was not able to prove this result. It was not until the 18th century that Leonhard Euler proved that the formula 2p-1 will yield all the even perfect numbers. Thus, there is a one-to-one relationship between even perfect numbers and Mersenne primes. Each Mersenne prime generates one even perfect number, and vice versa. This result is often referred to as the Euclid-Euler theorem. As of December 2015, update, 48 Mersenne primes are known, and therefore 48 even perfect numbers with 34,850,340 digits. An exhaustive search by the GIMPS Distributed Computing Project has shown that the first 44 even perfect numbers are 2p-1 for p equals 2, 3, 5, 7, 13, 17, 19, 31, 61, 89, 107, 127, 521, 607, 1279, 2203, 2281, 3217, 4253, 4423, 9689, 9940, 11,213, 19,937, 21,701, 23,209, 44,497, 86,243, 110,503, 132,049, 216,091. 756,839, 859,433, 1,257,787, 1,398,269, 2,976,221, 3,021,377, 6,972,593, 13,466,917, 20,996,011, 24,036,583, 25,964,951, 30,402,457, and 32,582,657. 4 higher perfect numbers have also been discovered, namely those for which p equals 37,156,667, 42,643,801, 43,112,609, and 57,885,161. Though there may be others within this range, it is not known whether there are infinitely many perfect numbers, nor whether there are infinitely many miscener primes. As well as having the form 2p-1, each even perfect number is the th triangular number and the 2p-1 th hexagonal number. Furthermore, each even perfect number except for 6 is the 3th centered non-agonal number and is equal to the sum of the first two halves odd cubes. Even perfect numbers are of the form with each resulting triangular number ending in 3 or 5, the sequence starting with 3, 55, 903, 3,727,815. This can be reformulated as follows. Adding the digits of any even perfect number, then adding the digits of the resulting number, and repeating this process until a single digit is obtained, always produces the number 1. For example, the digital root of 8128 is 1, because 8 plus 1 plus 2 plus 8 equals 19, 1 plus 9 equals 10, and 1 plus 0 equals 1. This works with all perfect numbers 2p-1 with odd prime p and, in fact, with all numbers of the form 2m-1 for odd integer m. Owing to their form, 2p-1, every even perfect number is represented in binary as p1s followed by p-1 zeros. 610 equals 1102, 2810 equals 111002, 49610 equals 11111002, 812810 equals 1111111002, 335503361 equals 1111111111111002. Thus every even perfect number is a pernicious number. Note that every even perfect number is also a practical number. Odd perfect numbers It is unknown whether there is any odd perfect number, though various results have been obtained. In 1496, Jacques Lefebvre stated that Euclid's rule gives all perfect numbers, thus implying that no odd perfect number exists. More recently, Karl Pomerantz has presented a heuristic argument suggesting that indeed no odd perfect number should exist. All perfect numbers are also Or's harmonic numbers, and it has been conjectured as well that there are no odd Or's harmonic numbers other than 1. Any odd perfect number n must satisfy the following conditions. N greater than 101,500. N is not divisible by 105. N is of the form n1, n117, or n81. N is of the form, where q, p1, pk of distinct primes, q alpha 1. The smallest prime factor of n is less than 3, either q alpha greater than 1062, or pj2 ej greater than 1062 for some j, n less than 24k plus 1. The largest prime factor of n is greater than 108. The second largest prime factor is greater than 104, and the third largest prime factor is greater than 100. N has at least 101 prime factors and at least 10 distinct prime factors. If 3 is not one of the factors of n, then n has at least 12 distinct prime factors. In 1888, Sylvester stated, "A prolonged meditation on the subject has satisfied me that the existence of any one such odd perfect number, its escape, so to say, from the complex web of conditions which hem it in on all sides, would be little short of a miracle." Euler stated, "Whether there are any odd perfect numbers is a most difficult question. Minor results. All even perfect numbers have a very precise form. Odd perfect numbers either do not exist or are rare. There are a number of results on perfect numbers that are actually quite easy to prove but nevertheless superficially impressive. Some of them also come under Richard Guy's strong law of small numbers. The only even perfect number of the form x3 plus 1 is 28. 28 is also the only even perfect number that is a sum of two positive integral cubes. The reciprocals of the divisors of a perfect number n must add up to 2. For 6, we have, for 28, we have, etc. The number of divisors of a perfect number must be even, because n cannot be a perfect square. From these two results it follows that every perfect number is an Or's harmonic number. The even perfect numbers are not trapezoidal numbers, that is, they cannot be represented as the difference of two positive non-consecutive triangular numbers. There are only three types of non-trapezoidal numbers: even perfect numbers, powers of 2, and the numbers of the form formed as the product of a Fermat prime with a power of 2 in a similar way to the construction of even perfect numbers from Mersenne primes. The number of perfect numbers less than n is less than, where c greater than 0 is a constant. In fact it is, using little o notation. Every even perfect number ends in 6 or 28, base 10, and, with the only exception of 6, ends in 1, base 9. The only square-free perfect number is 6. Related concepts. The sum of proper divisors gives various other kinds of numbers. Numbers where the sum is less than the number itself are called deficient, and where it is greater than the number, abundant. These terms, together with perfect itself, come from Greek numerology. A pair of numbers which are the sum of each other's proper divisors are called amicable, and larger cycles of numbers are called sociable. A positive integer such that every smaller positive integer is a sum of distinct divisors of it is a practical number. By definition, a perfect number is a fixed point of the restricted divisor function s equals sigma minus n, and the aliquot sequence associated with a perfect number is a constant sequence. All perfect numbers are also perfect numbers, or Granville numbers. A semi-perfect number is a natural number that is equal to the sum of all or some of its proper divisors. A semi-perfect number that is equal to the sum of all its proper divisors is a perfect number. Most abundant numbers are also semi-perfect. Abundant numbers which are not semi-perfect are called weird numbers.